Sometimes it'll work, a lot of times it'll work, but if you can't figure out what words to use to find the product, right next to that text bar is a little camera icon. You can tap that and try and recognize the product using computer vision. So we do a lot of machine learning, and we build a lot of data sets. And that's why we're here, because we've been using Mechanical Turk quite a bit to help us succeed. So I think, let's just, oh, here's the clunker. OK. So what to expect from this session, right? We're going to specifically talk about building machine learning data sets. We'll go over some best practices at smaller scales and at larger scales. And then a colleague of mine from AWS Recognition will come up to talk about the Recognition's experience in building data sets for that service. And as you may know, Recognition was announced today as part of the AWS AI package. What you won't get in this session is a detailed tutorial on how to use Mechanical Turk. All right, there's another session which covers that. But there are people in the audience from the Mechanical Turk team. If you guys can wave your hands vigorously. Yes. And you can talk to those guys afterwards if you have questions about the platform that I can't answer here. OK. So I think just as a quick show of hands, how many people here are actively engaged in machine learning today? OK. How many have used Mechanical Turk before? OK. Some. All right, and how many have any experience with computer vision in particular? OK, a much smaller number. All right, so I'll be drawing examples primarily from computer vision, but they carry over to other domains as well. So the key thing, one key thing to recognize about machine learning is that it's an incredibly competitive field. Researchers are moving like mad. They're publishing like mad. Companies are swapping and learning from the researchers, like mad. And as important as the algorithms are, they are reliably available. The state of the art is reliably available. What's also reliably available are the compute clusters you need. What isn't reliably available are large-scale, high-quality data sets, the things you need for training your classifiers. And that's where Mechanical Turk comes into play. OK, so for those of you not familiar with Mechanical Turk, you can go to www.mturk.com. What you see right off is that it's a marketplace with buyers and sellers, right? There on the left, you see the people. It represents the workers who are doing the tasks, doing the data annotation tasks we'll be talking about. And on the right are the requesters, the people who are publishing the tasks. That would be presumably you guys. So what is it? It's a marketplace for getting simple tasks done in parallel by humans. And the basic unit of work is a HIT. HIT stands for Human Intelligence Task. And an example of one might be you put an image up, display it to somebody, and you ask how many wolves are in this image. And they type in 3 or 0 or whatever it might be. All right? It's that simple, that's self-contained. You can ask more complicated things for sure, but that's the idea. It's not go research the state of the art in machine learning, right? That's not a simple task. All right? Now, requesters use Mechanical Turk either via the website or via an API, and they publish hits. And then they consume the results back from the workers. You can have more than one worker per hit, which, as you'll see, will be pretty useful. You have very rapid response times, and you get a pretty simple workflow. It's an HTML JavaScript template that you can put up, and then you have some a CSV file which lists the data that you want annotated, and you get a CSV file out with the annotations. So it's pretty easy to fold that into whatever workflows you currently have. OK, so the first question people have is, what kind of data sets can you build with Mechanical Turk? And I think the best way to answer this is to go to Google Scholar and just search for Mechanical Turk and machine learning. You'll get over 6,000 citations covering a wide range of fields from computer vision to natural language processing, psychology, even really hard things like argumentation mining, all right, are represented here. And so you can do all the key task types, open-ended questions down to binary verifications. And there's plenty of examples in the academic machine learning communities of data sets built with Mechanical Turk. Within the vision community, one of the most famous is something called ImageNet. It's a large-scale data set. It's got about 14 million images in it, representing 20,000 object categories. And it's been used by the computer vision community in machine learning challenges since 2010. So it just gives you a notion that that kind of scale of data set was readily available to a cache-starved academic community, as long ago as 2010. Okay. The second question, so that's what the types of data sets you can build. The second question people have is, okay, so what kind of quality can I get? It's a fair question. I'm going to break that down into 3 components for you. All right, so the first question is, how much do your categories intrinsically overlap? So if you're building a machine learning data set, you're basically doing some kind of pattern recognition, no matter what the domain is, speech, vision, what have you. And you've got categories of things. So for example, wolves and dogs, you want to distinguish them. Well, in real life, there's going to be some dogs that look like wolves. There's going to be some wolves that look like dogs. That's the intrinsic difficulty of your problem. If you're expecting the MTurkers to get this 100% right, you just can't. It's built in. And so one of your jobs is to actually take those categories and try and separate them as much as possible. And you do that by defining the problem, by varying the features that you use to characterize these things. Okay, so that's point number 1 about quality. Point number 2 is about the golden set. So you have some workers. They've gone off and done some work. You want to check the work. What does that entail? That means that you have to have gone and annotated some of the data yourself. That's your golden set. The trick is that if we take a look here, and I'm sorry that this room is split in this way. If I wave this around it, I don't know. Hope I don't blind anyone. Right? You have some space of, let's say, some space which represents all the true wolves that are out there. Your golden set is not going to cover all the true wolves. It can't. The whole point was to get a lot of annotations out of a large workforce because you don't have that large workforce, right? But you still have to check them. You have to go and build this golden set to check them, and you need to make sure that that golden set is representative of the true variation within wolves. If you don't, you'll have problems. Okay, so again, this doesn't have anything to do with the MTurk marketplace per se. This is you actually understanding the problem that you're trying to solve. The third issue, right, so we want that golden wolves to be, sampled from the full true wolf space. The third point is going to be about the workers themselves. How well can they solve your specific hit? So we have another region on the graph there that extends past true wolves. Those would be wolves. It includes wolves that the workers think are wolves that aren't really wolves. And it's up to you to design the hit such that what the workers think are wolves are all the way inside the true space. And there are control levers that Mechanical Turk gives you that allows you to pull off number 3, point 3. And I'll be getting to into those in some detail. Okay? All right. So for the rest of the talk, we're going to consider first building smaller scale data sets, and then I'll comment on larger scale data sets, and then I'll turn it over to my colleague Ranju Das to comment on recognition. Okay, so let's jump into smaller scale data sets. These are the types of things that you would be doing or should be doing a lot of. And the reason is that dataset construction is highly iterative. Okay? You're going to start by defining your machine learning objectives. You're going to source your data, which sometimes is quite difficult. Then you're going to get yourself into a loop where you say, okay, how are we going to annotate this task? What is the definition of the hit? What is our golden set? And then you're going to go and you're going to try it out, and you're going to see how well it works. And you're going to keep looping until you get something that you're happy with. And then you're going to go and augment your data. And then you're going to feed that into the machine learning algorithm, train and test it, see what the actual recognition rates are, and go through the whole thing again. And the reason we use Mechanical Turk is because that little red cycle there is something that we can iterate through very rapidly and very inexpensively. And we can do a lot of it. Okay, so let's start with an example classifier. So this one will be a classifier for the shape of a wristwatch. So imagine you're a large online retailer, and a lot of the goods sold on your site come from third-party sellers, right? So the site has watches on it, some third-party person has, or company has uploaded it, and their description has a text description and an image description. And you'd like to automatically determine whether or not those two are in sync. Okay, so that's something that would be a easier machine learning problem. And it's a classifier for a single feature, so data set would be relatively small, 2,000 training examples, the kind of thing you might get out of MTurk in an hour. Okay. Data source for us will be the Amazon catalog. And here are some examples of the kinds of watches that are in the Amazon catalog. So one with kind of a strange shape on the, I don't know if you can see that pointer on the far left here. One in the middle that's a little bit odd with a circular dial face and a square casing. And then, here's this, for example, on the far end. Oh boy, it's a standard watch. Okay, so our first experiment then will be to say, look, what's the simplest possible way we could build a classifier to solve this problem, all right? And that would be to say, look, from a customer's point of view, watches have one kind of shape. It's either circular, it's rectangular, or it's other. All right, so you can see how we've classified things. Okay, there we go. There's an example of a rectangular watch, classic circular watch, and then there'll be some in the overlapping regions. So for example, this one that we identified a minute ago as being a little bit strange, overlaps between circular and rectangular. Okay, so that's our notion of what the problem looks like. So what's the task that we put out on Mechanical Turk? Well, it's a web page, and it shows on the left here the watch that we want to have labeled. And on the right, it gives the worker three choices. It's circular, here's some examples. Rectangular, here's some examples, or something else. They click the radio button, submit, and done. In addition, we're going to show each watch to 5 different MTurkers so that we get differing opinions. Now, we might vary that number if we had a lot of questions as to whether or not MTurkers, how their judgments would vary. We might use 9 or even a larger number, and then reduce that over time as we understand the problem. But for now, we're just going to start with 5. Okay, so we run this. What results do we get? The result of this experiment is that the accuracy of the MTurk workforce is up around 97%. Okay, so this, what I'm showing you here is a standard confusion matrix. Don't worry about it if you're not familiar with them. But the basic idea is we took the golden set, which consists of 700 watches that we labeled with what we thought were the correct answers. And then we took the results from the MTurkers. And remember, it was 5 MTurkers per watch. So we had them vote. And we did majority voting. And we got an answer out of the MTurk pool for each of those 700. And 97% of the time, the MTurkers agreed with our assessment. Okay, fine. But imagine running this at a very large scale. 2.5% of millions of uploads could be a large number of errors. So can we do better? That's always the question we ask. Okay, well, remember that watch I showed you that had the square casing and the circular dial face? Built-in confusion. Our categorization scheme was too simple for that. So can we do something a little more complicated? All right, can we separate out the dial face from the casing shape? So instead of having 3 categories, we now have 16 categories. All right, 4 dial face shapes and 4 casing shapes. 4 by 4 is 16. What happens with this? We put that out to the MTurk workforce using this kind of a hit. All right, so again, on the far left, you see the watch that the MTurkers are evaluating. And now they have 2 choices, 2 sets of radio buttons, right? They have the dial face, they have the casing shape, and then they have the dial face shape that they have to choose from. Okay. Seems reasonable. What did we get? Accuracy drops. Almost 5%. Why the heck did that happen? Well, we thought about it. And our explanation was, without paying too much attention to the confusion matrix right here, but our explanation was that we started with 1 fuzzy feature, then we added a second fuzzy feature, and watches are really, there's a lot of variations in them, and what we actually did was create more opportunity for disagreement among the workers. So this was actually maybe not such a good idea. Now, there could be another explanation. It could be that a few workers were not able to make the kinds of judgments that we needed in the first pass, and here, asking them more questions exacerbated the problem. So there might be some issue with the judgment of the workers. Is there any way we could test for that? Okay, well, there is one trick. Well, there are actually many tricks, but the trick we used here was to say, look, are there any workers who are in the minority a majority of the time? All right, so you take a look every time a worker votes, okay? If they lost the vote, right, if 4 of the workers said circular and they said rectangular, then, okay, we say, you know, they're not doing so well. Let's just drop them. What happens? Well, we earned another 0.14%. So for this particular case, it was not the workers, right? It turned out that we had 124 workers going, and only 5 of them met this criteria. So it really is the fact that we added, you know, our modeling part of it, the machine learning part of it was broken. It wasn't the workforce that was broken. And some of you may have enough expertise not to be surprised by a result like this, but my team was surprised. It was a little counterintuitive. So one of the points here is if we go back all the way to this circle, that's the reason why you want to be able to try one of these experiments out in an hour, is to kind of really get to know the data, get to know the problem. If you can do that, you'll make progress much more rapidly. Let's see here. Okay, so I've just shown you 3 experiments out of many. I think the important point, though, here is that I really want to drive home that it's a myth that the dataset quality is an intrinsic property of the MTurk marketplace, okay? MTurk gives you some quality control levers. You can adjust your machine learning objectives. You can adjust your data sources. You can argue internally about what your golden set is, you know, whether a watch is other or really circular, that kind of a thing. And then you can vary the design of the hit. You can vary the workers that you allow to work on your hits. You can vary the number of workers per hit. You can vary your voting rules. You can provide workers feedback or not in various ways. Okay, all of those are control levers that you have to pull. Now, as a note, MTurk also provides you with throughput control levers. And obviously, the rate at which you publish work to the marketplace matters quite a bit, right? If you do it consistently, you'll have people waiting there for your work. You know, that's always good. But what surprises people a little bit is that price is actually more of a throughput lever, in our experience, than it is a quality lever, right? If the workforce is delivering 97% accuracy for you at 2 cents per hit assignment or a penny per hit assignment, going up to 4 cents per hit assignment doesn't get you 99%. All right? It'll get it done faster. Instead of taking an hour, maybe it'll take half an hour. I don't know. I'm just guessing there. Right? Because the pricing of the hit does influence how that hit is displayed to the MTurkers when they're searching for work on the platform. All right? But what you do want to experiment and see what the right price point is. There is a certain price point at which the workers will just not be happy. They'll say, this is too much work for what you want me to do. But in general, price is a throughput lever. And these other things are what you need to worry about for getting to a quality result. OK, so let me hit some of the best practices. Hit design, it's crucial, right? And I think at the heart of it are two issues. One is the simplicity of the question versus the clarity of the answers you're getting. You can put a very simple open-ended question up, how many wolves, and get a clear, apparently clear answer, 3, but what is a wolf, right? Should you have asked the question in more detail? Is there a 4-legged animal that looks menacing, has a long tail, and has, you know, fluffy fur or something like that? How do you do this? How do you communicate this clearly? This is something that you've got to experiment with. In general, we prefer questions with limited option sets to open-ended questions, smaller option sets to larger ones, et cetera. We're also always thinking about, look, we get some answers back. How do we aggregate them together? How do we do voting? If you have an open-ended question, how are you going to vote on that? You can't. You can really only take the union of it, the union of the workers' answers. The second major design tension is around ease of learning with the time to complete the hit. So these are fixed price hits, right? These guys want to move fast. So you want to think, if you have a lot of explanatory material that they have to wade through to understand it, that's going to slow them down. You have to think carefully about what that balance is. And one of the things that might not be so obvious is that every configuration of answers out of a hit should take the same amount of time to produce, if possible. It's not always possible. But if you have, say, choose 2 options, A or B, and if you choose B, you're done. But if you chose A, then you pop up 3 additional questions. Okay, now A takes more time. And you've built in a bias, right? So you'd rather tackle that kind of scenario by, say, using 2 hits. The first hit is A and B, and the second hit, you only run the ones that got A. Okay. Second set of best practices. This is around selecting workers. So Mechanical Turk has built into it a number of options that you can use to segment the workforce. Some of these are, up there with, because there's a number of people who use Mechanical Turk for surveys, and so this can help in segmenting the population for surveys. For machine learning, you'll very often have different criteria that you're interested in, and so you can cook up your own criteria. For example, you can look at the past performance of workers on your own hits. You can build custom tests of domain-specific knowledge or decision-making ability, whatever you want. But this becomes fairly critical. Another set of best practices exists around assessing the results. Okay, so I've mentioned that we typically use multiple MTurkers per task. So you have to have some kind of voting, but be careful. All right, your voting scheme, the results you get may be influenced by the prevalence of the categories. So for example, consider this. Suppose we were doing wolves and dogs again, right? And out of every 100 images we gave to the MTurkers, 99 were wolves and 1 was a dog. So if you're an MTurker, you can do pretty well just by answering wolf, wolf, wolf to everything. Even if you have the best of intentions, you're the most focused person, you're going to tend to miss the needle in the haystack. So if you do majority voting in that circumstance, you're going to probably miss the dogs. Right? So you might consider having a voting scheme where if any 1 or 2 workers spotted a dog, then it counts as a dog. All right? Now, you might also want to redo the whole thing so it wasn't 99% wolves and 1% dog. That's another issue altogether. But I just wanted to give you an example of a situation where voting may not be quite so straightforward. So think about, what the possible outcomes would be. Of course, if you have multiple options, you're also going to get split decisions from the voting, so you have to decide what to do about those. Now, the other thing that happens when you're assessing the results is this issue of worker feedback. You do have the ability to go in and approve or reject every single answer from every worker on every task. Now, if you have in mind that you're going to, in the long run, accept only workers who do well on your tasks, this could well be worth it for you to invest that time. But it is, it does cost you some time. You can't normally do that on a large scale unless you have a golden set. If you have a golden set, then you can basically reject any hit that contradicts the golden set, and then they get the message. They learn that way. All right? But you need to think about how you provide feedback to them. I guess you can also adjust the selection criteria. And I think the one thing that people may not realize is that the workers actually communicate quite a bit on forums. They're not Amazon forums. They're their own forums. And you can read those forums to get a sense for what they think of the hit. Is it difficult or what have you? And that can be very valuable information. All right, so to summarize here, the main points to keep in mind when boosting quality: 1, separate your categories, right? Reduce the intrinsic difficulty of the learning problem. If you don't do that, don't expect extremely accurate results. In fact, don't even expect your own teams to be able to agree on what the golden set looks like. All right? Secondly, build a golden set and scrutinize the false positives and false negatives you get from the MTurkers. Where are they making what you think are errors and why? How can you vary the hit design? Can you simplify and clarify your instructions? What can you do? What are the levers can you pull to improve the result? Optimize your worker qualifications. And then finally, just experiment a lot. Okay? Machine learning, it's pretty basic. Garbage in, garbage out. All right, so the accuracy with which you built this data set is going to put an upper bound on the performance of your machine learning classifiers. All right, so let's switch now to larger scale data sets. So let's suppose you've gone through this process at a small scale and now you want to worry about getting big. So we're talking about millions of annotations at this point. The first thing you have to think about is measuring quality over time. So suppose we have a situation where you want to build a data set of 1 million training examples. You're going to release them at 100,000 a week. Okay, because your own team can't consume the results faster than that, right? So you could put them out there as a huge batch, I guess, but you'll probably want the opportunity to look at what you're getting back. And let's assume that you want a 99% confidence level in the accuracy rate. We know right off that the interval, the confidence interval, around that confidence level is going to vary with the sample size. But we also know that it doesn't really matter if it's 1 million or 100 million. You can pick 2,000 samples and get 99 plus or minus 1% or so. All right, so let's just assume that we've chosen our sample size over the full set at something on the order of 2,000 samples that we're going to check. So now you still have to think about what your strategy is. All right, one strategy is to have the workforce produce all the annotations for you, and you check it at the end. You randomly sample, you go and you look at the results of the 2,000 samples. If you do that, you haven't been able to provide feedback earlier on. Okay, so maybe you're going to sample over the 10 weeks 200 examples every week. Now your confidence interval is going to start out big and shrink down. But you can provide feedback to the workforce earlier. Maybe that's what you want to do. Or you could sample, put the golden set in all 2,000 samples at the very beginning, scrutinize everybody carefully, and then trust them after that. That's another strategy. There are people who use that third strategy, the second strategy, and the first. It depends on your circumstance. I will say that one additional strategy that we do use is to partition your workforce, okay, into, say, two groups. And you have a golden set for the first group, and they get up to speed. And then you use them to build a golden set for the second group, get them up to speed, and then they can generate a golden set for party A, and you can flip back and forth. At first blush, you might think that it ends up being the same amount of work, but in fact, if you have workers whose accuracy you understand, it does end up saving you work. It's faster to judge the results this way. So we use that a lot. Okay, so this brings me to the second myth that I'd like to dispel. And this is particularly important for the large-scale data sets. So this is a result out of the Stanford AI Lab this year. And the concern is always that if you have people working over millions of annotations, that they're going to get tired of it, and their quality will just go down over time. So what you see up here are plots of individual worker performance. So the vertical axis is the accuracy of the worker, and the horizontal axis is time over the course of the project. And these were multi-month long. Actually, this data is taken from I think it was 4 months, but a multi-month long project. And what you can see is that the worker's accuracy does vary. So for example, up here in the upper left, you have a worker who seems to be averaging around 95% accuracy, and next to it is one who's a little bit less, seems to be closer to 90% accuracy. But in fact, what you don't see is that over time, the accuracy is going down. It's stable. So that's pretty good. Okay, the next challenge, minimizing cost. When you're building a data set with 2,000 examples, at a few cents a hit, there's not a lot of cost involved. At millions of examples, there is. And so what we do is we don't worry so much about minimizing the cost per hit. That's a bit of a false path to go down. What we do is we minimize the cost per training example. Okay? So suppose that you had a task of recognizing 20,000 categories of objects. Your data set needed to have 1,000 examples of each object. So you're looking at roughly, if I do the math, I don't know, let's see, 20,000, 1,000, 2 million examples. No, more than that, 20 million examples. That's quite a bit of work. If you were to pipe, set up a hit, which basically checked and this would be crazy, right? You wouldn't do this. Please don't do this. You take every image in your stack and you pipe it through one hit and say yes or no, is it in one of these 20,000 categories, right? That's a very simple task. It's a yes-no task. It's a verification hit. but you'd have a lot of them to do. You want to divide and conquer, all right? And you want to worry about your validation rate. That's what made my first example so crazy, right? The validation rate is the percentage of things, it goes back to wolves. If your question is this a wolf, yes or no, and 99% of them are actually wolves, then your validation rate is 99%, okay? That's cost effective. If your validation rate is the flip, if it's 1%, now you're paying people money to look at pictures which don't contain really very frequently the thing you're looking for. So top-down approach, instead of going after the 20,000 categories, start with 10 super categories, right? And put things into rough buckets and divide and conquer on your way down. Or bottom up, right? Do some clustering, some automatic clustering of the images from your data source, and then have the MTurkers label those clusters. And then verify the contents of the clusters, split the cluster, and work your way back up. So those kinds of approaches. All right? These kinds of approaches usually involve a team. But it's a large-scale data set, so that's to be expected. All right. As a final point at building large-scale data sets, I want to say that success is an issue. All right? No matter how thoughtful you are, how good you are, if you're building a real-world system, eventually your user input, your users are going to give you stuff that you haven't trained for. You're going to fail on it. So the first thing is to know when you're failing. That means that you're going to have to sample from what the users give you and what your system produces, and with humans, check and see how well you're doing. Right? How have the query images in a vision example deviated from what you expected? And then you're going to have to use those errors to expand your test and your training sets, and you're going to go around the circle again. All right? So this circle is your life if you're doing this. All right. So with that, I'm going to pause and introduce my colleague, Ranju Das from Recognition, and we'll have time for questions at the end.
Thanks, Peter. It's fun, these post-lunch sessions, right? You guys are all so excited. I'm here to talk to you about Recognition, mostly about MTurk in relation to Recognition. We announced Recognition this morning. Andy talked about AWS trying to find meaning within your data. And Recognition is specifically designed to find meaning within your images. And we believe that we have been able to do that largely because of the enablement of MTurk and the workforce that comes into play with MTurk. And it's a proof that everything Peter talked about, it actually works. And I'll walk you through that a little bit. I'll talk about some of the challenges that we initially faced and some lessons that we learned from it and some success stories around it. I'll try to avoid words because I think Peter kind of covered my set of words. So mostly work on images here. At Recognition, quickly, it's a deep learning-based image recognition system. 4 primary capabilities that we announced this morning: objects and scene detection, facial analysis, face comparison, facial recognition. I'll shamelessly plug my MSc203 session at 2:30. Please join me if you want to know more. But what's important to understand here is it's a deep learning-based system. And as Peter talked about, deep learning-based systems heavily relies on high-quality data for training as well as for testing. And when you're building a service of our scale, where we are delivering it to all AWS developers, thousands of labels, high-quality face detection, high-quality face recognition, you need to generate a massive amount of ground truth data. And I do not think we could have done this without the enablement of MTurk. Now, what's interesting is that when you start with MTurk, because the team does such a fantastic job of abstracting the human from you, the APIs and the workflow is so brilliantly designed, you kind of get fooled into the fact that there is human being at the end of it, right? And we learned that the hard way. it was important for us because what we were dealing with is a bunch of images, and it inherently got into this problem of how we as human beings, forget MTurk, all of us see things. And we, in our vision system, there are two parts. There's an inferential part and there's a referential part. The referential part is actual activation of neurons. The inferential part is what we use our experience, our distributed data in our kind of brain to see what's in the image. Why is that important? Why is that important when you're using MTurk? What do you guys see here? Anyone? Hat. Yep, that's what you see. Because you've looked at a very localized region of this image. What do you see now? Baby. MTurkers absolutely immediately saw baby. So what's very interesting here is that people are really not good in classifying region proposals. It's not inherently natural because we are always applying all context. Our brain was inherently designed for survival, and entire context of the scene is important for us. So there are some interesting human bias that shows up when you deal with large amount of images. And we had to deal with hundreds of millions of images. Very happy to share with you that we were able to scale, and it wasn't any capacity issue on MTurk. We just didn't have enough images to deal with. At peak, millions of annotations per day using MTurk, right? So we dealt with a lot of images, a lot of annotations. Human being, the inferential part, if you may, we like to see things that are not there using our experience. So human being typically, and not only MTurk again, I'll keep saying this is not only specific to MTurk, human being would like sees baby in this picture. So we send it to MTurk, we send it to external, we send it to QA, we send it to our own people. Everybody saw a baby in this image. Of course there is, just hidden. Everybody saw a fish here. Everybody saw a ring. I was thinking there'd be a gender bias in this, that the female gender would probably see more rings, but apparently men also saw a ring in this picture. We also tend to bet the whole from the parts. You take a part of the image, you don't get to see the whole context, but you tend to bet on the whole. So for a good example here, everybody saw a baby, everybody saw a newborn, everybody saw a child. This was surprising. Guess what people commonly tag this image with? Any guesses? You guys are brilliant. Or human. This one just gets me. So this is where, you give this image to human being. They, of course, find baby. They find birthday. They also see, who can guess? The invisible. Balloons. Because of the strings in the back. So now if you trained your models using this image, you're training your model to look at either strings or hat and think of them as balloons, right? So why is this important? Again, to kind of tie it back to how could you use this, right? Design your hits, as Peter talked about. Make sure you are using consensus, right? Because if in some cases, we used 3 MTurkers to vote on a particular image. In others, we went up to 5, because there is this inherent bias, and you want to capture as much information from the MTurks as possible. We also love text hints. We trust text hints more than anything else in images, and it's such a natural human bias. Guess what all humans saw in this? Farm. I mean, it goes to figure there's probably a farm there, but they were so sure 5 out of 5 MTurkers saw farm in here. No greenery here, by the way, but they saw farm. Chocolate. They found a chocolate in this image just because there was this text hint that there's chocolate. And I'm gonna be impartial to this thing and not use this red light thingy so that both of you guys are equally. Guess what people saw in this image? Pizza. They did. And we love our stereotypes. And they are amazingly complex because they have cultural bias, they have geographical bias. When I came to this country, I would have seen a bunch of people just being silly. But now I know this is beer pong, and people saw beer. There is no beer in this image, right? Again, the cultural stereotypes are important. The symbolism is important. All MTurkers annotated this as 4th of July. This came on as party. And then this is the other piece, right? We have a tremendous amount of experience. The more wise we are, the more we tend to think that we know things what happened before and after, and it shows in inference of images. And so every MTurker and every human being sees this and tags this as swimming. This, any guesses? Wedding. Well done. This is hiking, camping. Though you don't see the actual activity, it's clearly obvious that these people are camping and they're having their camping meal. So how can you help MTurkers? Oh. Is it playing? How do I play the video in this thing? You think I know how to do this, right? Well, provide. I did. There it is. So provide reference to Turkers. Show them what you want them to see. Providing that simple strip of images that are reference images improved quality by over average of 10%. And they were much more accurate in detecting the things that you want them to detect, right? So in this case, think of the balloon. We actually had actual balloon, different shape, different size, and also said when it's just strings, it's not a balloon. So you want to kind of train them a little bit in situ, in the experience, in the visual flow, how it works. And you tend to get fantastic results from it, right? Make the questions very simple. Make the questions very direct. Is it an object? Is this, do you see this in this photo? Make the call to actions very simple, right? A simple yes, no button. There is no other clutter. You could skip, but it's a small thing. Everything else is kind of, if you look at the design, the call to action is look at the major image and say yes or no, right? So simplify the experience for them. Let's see if I can do it this time. Apparently not. Okay. Same here. This is a bounding box generation example, and we gave what we want the dogs, what sort of dogs and how it would look. The key here we found when we did the first rev, the bounding box were not editable, and human being likes to tweak. They draw a bounding box. They would like to quickly go back, identify the bounding box, change it, and reshape it. So as you think through these sort of object localization examples, think of how you can make it editable, how you can make it so that the MTurkers do fix the issues that they find, right? Again, the key here is that they actually are very, very incentivized to do good work. It's our job to make sure it's possible. It's our job to make sure that the experience is simple, it's minimalistic, and the call to action, again, see, a single primary call to action. You draw a bounding box, you say next, right? No confusion. You have examples out there that shows that. Some new things that we are playing with is, can we show a cluster of images? And we want to see how human being deals with it, because it is obvious that even if you don't know how to look for a dog, if you see similar shapes, we are very good in shape matching. So if you could find high quality, similar clusters of objects and put it in front of them and ask a question, we want to experiment with that. We want to see how they perform, right? So summarizing kind of all of this, Peter said much more eloquently and better with a lot more data. So risk of looking a little silly. We did find making the hits bite-sized is important. It's not about the fatigue that Peter showed. It really isn't doesn't exist. For us, it was about the hit size helps us measure quality. And the smaller the hit size, more real-time our feedback loop could be, right? So 100 images with enough control data that we know how the MTurk is performing helps us manage the workflow a lot better. Clear and concise instructions. Provide them very clear instruction. The questions have to be simple. Ask, as Peter talked about, create a voting system, build consensus. Complex object, you might need to extend it. We started with 3. In some cases, we ended up to 5 MTurkers. Include, as I said, control images, known golden set. So we know in situ, in real time, how an MTurker would perform based on the 5 true positive and negatives that we send in every hit. And so then use that data to qualify and then work with the MTurk team here to whitelist, blacklist, give feedback to them, share the data with. One of the biggest myths on our side, on recognition side, is that for the first few months we were adventurous. We thought we knew what we're dealing with. And then we realized we don't, and we went begging to the MTurk team, help us. And as we shared data, we got much better response, much better service, even from the workforce. So thanks. Thanks for spending the afternoon. Any questions? Peter, do you want to?
How many minutes do we have?